Thanks so much, Edith, and thanks for all the organizers for inviting me here. So it's also thanks to Oliver for having such a good introduction to what I was going to say. So I have two roles as an infrastructure director for National Infrastructure for Science for Life, and now as a new role in director of the data-driven life science program. And then I am a cancer researcher. I put my cancer researcher hat on as well. So SciLife Lab provides all the technological wizardry that there is today to help scientists to do their research. And obviously, this is particularly to do systems biology and combine the capabilities. This is the new addition that we are highly excited about and have been collaborating a lot with EMBL on this. What is there in data science and data-driven research that we could do over the next 10 years that really would make a difference? That's what we've been thinking about. And obviously, it doesn't, don't have to think hard that it's AI is one of these things. So my part number one is a little bit of a generalized AI issues. Part two is more complex. That's a bit like the Oliver story on data-driven translational research. How do we deal with it? As of 4 months ago, I was converted. I saw the light. I started to preach Vatican terminology about the impact of AI for the average life scientist. Because in a way, I feel that we all need to apply AI in everything that we do, to understand literature, analyze data, even learn to write code, help to write papers, help to write grants, evaluate grants. And I've done all of these things, and I try to make everybody in our community to do this, because me as a cancer researcher with AI is 2 times better than me without AI. And I think it's particularly the multidisciplinary expertise that we can bring out of that that really helps. But what I do always, also in strategy, as a director, I ask the AI all sorts of questions like, give me 7 strategies to help inequalities in cancer therapeutics, care and prevention. There comes a perfectly reasonable answer. And think about the point number 4 there that we were just discussing, improve cultural competency in cancer care. Just get it from the AI. And it also can help you to do that in a context-specific manner. How would that work in a developing country setting? And obviously, the answers are quite different. Like you need to increase awareness and work with access barriers and so forth. I also asked, well, what about data science? What can we do with data science to help with the inequalities? And again, do it in the industrial country setting and developing country setting. And absolutely fantastic answers, and I'm not going to read them through you. You can all query AI today in that sense. But like leveraging the big data, employing machine learning and so forth. But what is really interesting in a developing country setting is how much of mobile health and digital technologies would actually help in that context, and how the answers that you get are actually helping to put that perspective. Like using AI, number 5, to support clinical decision making. When you don't have the expert, that's when AI can really help most. And we can probably do a lot of. So what are the fantastic technologies? Also, the technologies that help us in the Western world are different than those that would help us in the developing world. So interesting insights that you learn from AI. And just to kind of wrap up this part, this generalized AI has been set, which can be debated, has the medical examination bar in the US. Obviously, it's not performing like a physician, and this is still the early days. But that's not all. It also has passed the bar for law and business. And if you just test it, it would pass the mathematician, statistician, programmer, chemist, physics. So you, in a way, have in your pocket a multidisciplinary expert that you could resort to. And I think we are grossly underutilizing that opportunity that we have with us. So this is something for cancer centers to think about in research and in the future, in the more difficult area of helping physicians. What is also there is the patient empowerment, and I stop here in terms of this part, because I think this is actually really an interesting opportunity where every patient will have the same access. Every patient will be able to resort to all of these capabilities. And it starts to resemble to me a multidisciplinary panel of experts that would help each patient. But now that we have staff shortages and can't get everything maybe done, this is where generalized AI can really empower the patient. And this, dear colleagues, is reducing inequality if you can access. So that was part one. Part two is sort of a continuing a little bit where Oliver left, and this is more complicated, obviously. And I raise only 3 issues on sort of a challenges in translational oncology. One is to work on these death valleys or gaps, as we talk about, either between research and clinic or clinical knowledge and clinical implementation. And one aspect that I want to point out is that this is actually a lot about prioritization. This is not just about translating, but this is about how you go from 10,000 molecules to one biomarker, how you go from 10,000 leads to one drug. The scales that we have in research and in the clinic are totally different in most cases. And then the other point that we often bring all our baggage of previous information, previous knowledge, previous technology to it. And that makes actually things slow and cumbersome. And then the third one is obvious that now that we have sort of been going through genomic subgroups as a means of attacking interesting patient groups, they are getting smaller and smaller, and this is getting more and more difficult. So if we are now starting to put additional information, layers of information on the clinical data, we have genomics pretty much routine in many places. We're starting to put proteomics, other technologies to it. Obviously, amounts of data continue to grow exponentially, and we hope that the patient benefit continues to grow as well. But then at the level of translation, this is actually a huge prioritization step where we would not like to lose the patient benefit. And that is obviously the challenge, that how can we create clinical biomarkers that replicate a lot of that. Now I stopped advancing this for some reason. How they replicate most of our information in this deep, deep omics data. It doesn't help if we just put more stuff on the left if we can't prioritize things on the right. So our example, and I'm just reflecting our ongoing research here, was to take a data set that we've assembled in AML, acute myeloid leukemia in Stockholm. 60 million data points covering the same types of things that Oliver was just showing across different omics capabilities, and narrowing that down to the degrees of 11 independent dimensions of variability in the data, which we now call data-driven hallmarks. Again, thanks, Oliver, for pointing the hallmarks of cancer. I'm not talking about the hallmarks of cancer. I'm talking about data-driven hallmarks in AML. And this has been a conceptually interesting case, which I've kind of presented to you, but also sort of something that we would like to promote for translation in general, that you can identify these hallmarks, focus on the hallmarks, what they do, and you do it unbiased. You don't take into advantage of anything that is known before. This is totally unbiased. And you combine all of the various omics layers, so you are not biased to working on genomics or proteomics. You pick up what are the aspects that are best identified there. We've also been doing ex vivo drug sensitivity testing on all of them. So every hallmark is linked to specific drugs that work on that hallmark. So this takes a hallmark classification and links drugs to it, which would be fantastic for precision medicine and also for developing combinatorial treatment. This obviously looks so much more sort of clearer to you when you look at it in a hallmark setting rather than looking at it in a classical hierarchical clustering where you're trying to fit everything together, and they don't, because cancer have independent properties and they align among that property, but they don't align between subgroups. And therefore, this looks really neat in many ways. It replicates many of the known features that we already have seen in cancer, such as that monocytic differentiation is a strong predictor of venetoclax response in AML. And what is really neat about this as well, that we can then form a hallmark description of each patient. So each patient has a value for these 11 hallmarks. These are specific numbers. These are not just the properties like in the Weinberg definition. And like I said, if you have hallmark 2 that is low, then you respond to venetoclax. If your hallmark 2 is up, you have resistance, but you may be responsive to MEK inhibitor. Interestingly, there's only one of these hallmarks that associates with clinical information and prognosis. And it actually replicates pretty much the ELN risk classification. So without actually having the genetic strong component there, it actually allows us to pick up a few markers that predict prognosis in AML as well as the ELN classification, which is quite amazing, really. So in a nutshell, and I'm finishing up here, I see that I was rushing because I have good time to finish my last remarks. This is not just that you don't mix this up. This is not the hallmark classification from Weinberg and Hanahan that you just heard about from Oliver. We are developing our own hallmark specific for AML. These are not just properties and concepts, these are actually tied to molecules and pathways, and they are linked to drugs in patients. So I think that this is an interesting, even though I know that many of you are working on similar types of things, but it's an interesting way how we think that in the future we may be more systematically able to work on prioritizing biomarkers in the way that I showed in the graph, and that this would not cost 4 million euros to do, but this would be a bunch of biomarkers developed against a limited number of hallmarks in each case. So this could help already, based on this information, tailor therapies. This could already help to identify patients at risk. And this would not need the millions of euros and high expensive instruments to do this. And this, my colleagues, is reducing inequality. And I stop here. Thank you.